Today we're going to be looking at a question where a suitcase is going to be sliding down a ramp and then on across a floor an additional distance. Okay, when it starts sliding down the ramp is frictionless, and so it'll slide down the frictionless ramp, it'll pick up some speed, and then it will slide across the rough floor where, of course, it will be acted on by friction, and so it will lose some of that speed. In fact, it'll lose all of it. Since the beginning of that is frictionless, we'll be using a conservation of mechanical energy idea for that. That's the idea that the mechanical energy at point 1 is equal to the mechanical energy at point 2. Now remember, this idea is only valid if you're in a situation where there is no friction. Okay, and so we'll be taking it from this point, point 1, and we'll be sliding down to here to point 2. And since that occurs along a frictionless ramp, the conservation of mechanical energy is valid, and we'll look at that. This corresponds to questions 4, 5, and 6 on the Work and Energy Part 2 homework. All right, so I'm going to read that. Starting from rest, a 10-kilogram suitcase slides 4 meters down a frictionless ramp inclined at 30 degrees from the floor. The suitcase then slides an additional 5 meters across the floor before coming to a stop. And we have all of our givens and the fact that the acceleration due to gravity is 9.81 meters per second squared. And question number 4 asks us to find the speed of the suitcase at the bottom of the ramp. And so I'll label that as v2, meaning the velocity at point 2. And that'll be what we'll start out by looking for. All right. Now, since it's going to slide along the frictional ramp, we'll use our conservation of mechanical energy ideas. Now, that means that the total mechanical energy, which is the sum of all the potential and all the kinetic energies at each point, are equal. So GPE1 plus KE1 equals GPE2 plus KE2. Now, of course, elastic potential energy would also be included on each side if there were any, but there's no rubber bands or springs or anything else to provide elastic potential energy, so I have just left it out on both sides. All right. Now, in this case, it starts with a certain height, a certain elevation above what we'll call our reference point here at the ground. And so GPE is found by taking the mass and multiplying by the acceleration due to gravity and multiplying by the height. Now in this case, the height is actually the height above the reference point, or above the surface. And so that's going to be this distance here. And we'll come back to that again in just a moment. We'll also add the kinetic energy it has. Well, since it's at rest, it starts at rest, that kinetic energy is 0 joules. Now once it slides down the ramp, well then it will actually be at the reference point, and so the height will be 0. So the gravitational potential energy of an object at the same level, at the same elevation as the reference point, is 0. So 0 joules of gravitational potential energy at point 2. However, it is moving then, so it will have some kinetic energy, and that will be equal to 1/2 times the mass times the velocity at point 2 squared. Kinetic energy 1/2 mv squared. All right, and so at this point, since we have our mass, we know g, all we need is our height in order to be able then to solve for velocity number 2. In order to find the height, we're actually going to use our trig functions again. Since we know this distance, the distance along this hypotenuse, it's 4 meters, we can just right down here say, let's see, tell you what, we'll say that D1, the struggle tonight. Let's see, D1 sine theta is equal to h. In other words, we'll use that hypotenuse and the sine function to find that imaginary distance, well, that actual distance right here, which we've labeled h. So d1 sine theta equals h. Now, with my numbers, once I do that, I find that h is actually equal to 2 meters. So I'll put that in my formula over here. Mass of 10 times our gravitational acceleration, 9.81 meters per second squared, times our height of 2, and that is going to be equal to, that 0 of course is in there, as is this one, but we can add 0 in our heads, 1/2 times 10 times velocity 2 squared. All right, and when you perform all that work, you end up finding that the velocity is equal to 6.2642 meters per second. And again, that's more decimal places than really would be reasonable, except we're submitting this number to a computer, and computers are not entirely reasonable. So they just do what they're told, and it's going to be checking to within 1%. So you'll need to enter several decimal places to be sure that you're within 1% of that value. All right, so there's part A, check. And then we'll move on to part B, and it says, find the coefficient of kinetic friction between the suitcase and the floor. All right, so at this point we're looking for mu. That is the coefficient of kinetic friction, so we could say mu k. Now, in this case, and in all cases, remember that mu is equal to Ff, the force of friction, divided by Fn. Okay, so in order to calculate mu, we'll need Ff and Fn. Well, Fn, remember, once our object gets down to there and then begins to slide across, the floor, well, at that point it's on a flat surface, and so the force of gravity acting on it will exactly be balancing out the normal force provided by the floor. Or really, we should say the normal force provided by the floor will be balancing out the force due to gravity. So all we need to do is find Fg, and we'll have the value for Fn, which we could substitute there. Remember that the way we find Fg is by taking the mass of the object and multiplying by 9.81. In this case, with a mass of 10, you don't need to get the calculator out. We can quickly see that that Fg and Fn will both equal 98.1 newtons. Okay, and so that will be Fg and Fn, and we'll just save that to substitute in just a minute. So now we need the force of friction, and that's a little more tricky, except when we think about our energy ideas, remember that, okay, it has a certain amount of energy here at point 1, and since it slides down a frictionless ramp, it still has that same amount of energy at point 2, but then it moves along the ramp and is subject to the force of friction, and so by the time that it arrives at point 3 here at the end, it has come to a stop due to friction. And so in this case, what has happened is all of the energy that it had here, gravitational potential, which then was transformed into kinetic, has now been used or spent doing work against friction. And so all of that energy is lost to friction. That is, it is spent or expended doing work against friction. So the energy that it had at 1, which was this amount, and in my case that actually ends up being equal to 196.2 joules, the amount that it had here, the same amount that it had here, is the same amount that will all be spent doing work against friction. And so all of that energy is actually equal to the work done by friction. So the work done by friction is equal to the energy lost, and in our case, that's all of it, and that's going to be 196.2 joules. Where did I get that? Well, that's the number that I actually calculated right up here when you multiply 10 times 9.8 times 2. And so the work done by friction is equal to that, and it's 196.2 joules. Now, another way to express the work done by friction is the Remember that all work is force times distance, so if you want to know the work done by friction, you need to know the force of friction times the distance. So we still have work as force times distance, and of course remember that that always needs to be the force that is parallel to or in the same dimension as the distance covered. In this case, friction acts parallel to the surface, so it is in the same dimension. Well, the work done by friction was 196.2. So 196.2 is equal to FF times, and in this case that's D2. And so that is equal to 5 meters. So then if I take 196.2 and divide by 5, I'll have the value for the force of friction. And it turns out, if you do the math, that's 39.24 newtons. Again, using my numbers, your numbers will vary. So let's take FF and Fn now and substitute them into mu and see what we find. And as we substitute FF, 39.24, and divide by Fn, 98.1. Remember that Fn is exactly equal to the force due to gravity. We find that the value for that is exactly 0.4. Now, honestly, to get an exact number of 0.4 is a bit unusual. Typically, I would expect you to have that. I would expect that not to be such a nice, neat, round number. I would expect there to be other numbers there. And remember, when you're entering that into the calculator, or into the computer, you'll need to preserve at least 4 digits past the first non-zero digit. So in this case, we would then look to have at least 3 more decimal places to be sure we were answering within 1%. All right, so be careful about that. I don't want you to enter too few numbers and miss the problem because of that. All right, the last part, section number 6, asks for the change in mechanical energy due to friction. And it turns out we've already got the answer to this because it had a certain amount of mechanical energy here, 196.2 joules. It had that same amount at point 2, 196.2 joules. And then at point 3, of course, it has 0 joules of mechanical energy because it has no elevation, so no GPE. It has no motion, so it has no KE. So what happened to all that 196.2 joules? It was all spent against friction. You've spent it all, every bit. I hope you're happy about that. And so it turns out that when they want the change in mechanical energy, well, it lost every bit of it. And so the change in mechanical energy is actually equal to the negative value of whatever you had earlier. Because since all of it was lost, then the change is that amount. And since it is a loss, that's considered negative. All right. I hope that that was helpful and that you'll be able to work those now. Please remember, as you're working others in this homework assignment, the idea that mechanical energy lost is equal to work done against friction is an extremely important concept that oftentimes will allow you to calculate the force of friction when you don't have any other way to do that. Or if you know the force of friction, you can find the work done against friction and you can calculate the change in mechanical energy. So you can either use the loss of mechanical energy to know the work done against friction, or you can know the work done by friction to calculate the loss of mechanical energy. So very important idea there. All right, hope that's helpful. Thanks for watching.